Okay, let's maximize this. Okay, so last time I tried to get through towards the end of the lecture this time derivative of this expectation value thing, but I think it's a good idea for us to just get a better sense of what this expectation value operation is actually doing. Okay, so in Thomson, right, it's just when he writes the expectation value, he puts these little what is it, alligator brackets around it, right? And this is known as a bracket notation, right? Where if you want the expectation value of let's say, I don't know, momentum in the x direction, for example, you would do that. And this is actually signifying, right? You have some wave function on the left-hand side, and then the operator in the middle of it, and then the wave function on the right-hand side. And the left-hand side and right-hand side of these wave functions are actually slightly different from each other, where this is actually just the regular psi, but this is actually the psi dagger, where this dagger thing, right, means it is a transpose and the complex conjugate of it at the same time. Okay, it's just doing those two operations at the same time. And we're going to see a solid example of why we need to do this in a second here, okay? But that's the idea of this expectation value, is that when you're writing this little bracket stuff, you really mean writing this stuff. It's just a shorthand to write it, okay? All right, so let's do an example in matrix form, because in matrix you can just see how the matrix and the vector actually work, right? Remember, I think those like late last week, right? We talked about like eigenvalue, eigenvectors and stuff like that, right? And eigenvalue, eigenvectors are special in that if you have some matrix, right, and you multiply it with some vector, right, the eigenvalue, eigenvector is the ones that you get the same vector back, so you don't rotate that vector at all, but it just gives you an eigenvalue lambda, so it's just kind of scaling that vector, okay? The example I gave last week was this 1, 4, 3, 2 example, right? And I told you what the eigenvector is -4, comma 3, right? When you do this multiplication, you get 8 minus 6, and thanks to Shane for correcting that, right? Okay, if you factor out a -2 here, right, you get the same vector back, right? That's the idea, okay? So the eigenvalue is -2, the eigenvector is -4, 3, okay, right? So let's just do an example of what happens when we try to calculate the expectation value of this matrix A out of here, right? Okay, I'm going to see that it's actually just the eigenvalue, okay? So this, we're going to find that, oh, since we know the eigenvector for this particular matrix is -4, 3, right? I'm going to define a wave function, right? I'm going to put a 1/5 in front of it. And that's just because I want this wave function to normalize to 1. And we're going to see why that's the case, okay? And right, and this is the eigenvector that we already know exists, right? The dagger version of it, right? The complex conjugate and transpose of it, right? It's the same thing, but as a row vector instead, right? This is a column vector, this is a row vector, right? The complex conjugate doesn't do anything because they're real numbers in this case, right? But in general, there could be changing that that I to -I, okay? Okay, right. And you can check that if you do psi star psi together, you get 1, okay? That's just to normalize it to 1. It doesn't have to be normalized to 1. So if you have 2 particles, maybe you want to normalize it to 2, 3 particle, and so on like that, okay? But our operator, right, is this A, which, in general, can be anything, but in this case, let's just make it a 2x2 matrix. And technically, I think this doesn't work because it's not Hermitian, but, let's just play around with the matrix for a little bit, okay? So if I do the multiplication of this matrix with psi, right, so psi is here, A is here, right, this is my operator, this is my wave function, all right, okay? If I do that multiplication, right, I end up with I think that 1/5 should still be up front, right? And I think I made the same mistake as last time, right? So if you do this multiplication here, just keep the 1/5 in front, right, then you get 8, -6 as the resulting vector part at least, okay? Okay, and then if you factor out this -2, right, once again, you get this eigenvector back, right? So the result of this operator, this matrix multiplied by this is just -2/5, right? -4, 3. In other words, it's just -2, the original wave function back, right? Right. So, but that's the idea of these eigenvalue, eigenvector, right? So this, whatever this operation is, right, gave you a result of -2. Okay, but if you sandwich it with the psi dagger also, right? So that's adding this row vector on the left-hand side here, right? And then the original, the one that we already computed up here is the a psi, okay? And we do this this row vector times a column vector multiplication, right? You're just multiplying these two numbers together, plus these two numbers added together. Then you get 25 as the result. And what happened is that these 25 actually cancel out. So you get 2 as the result, okay? Okay. So the expectation value of, this matrix with this wave function is -2, okay? Well, proportional -2 because there's some integral involved, but let's just think about that, okay? So that's what these, bracket notation and then psi star stuff is actually doing. Just think about that as a concrete example, okay? When we have to deal with other types of example, it's not as easy to see, right? But that's how you want to think about it, okay? This is just a column vector. This is a row vector. This is some matrix between the two, okay? Thing I was trying to derive yesterday is that, well, how does this expectation value change with time, okay? So when you want to figure out whether or not something changed with time, you take a time derivative of it, right? If that time derivative is 0, that means it's a constant with time. But if it's not, then you figure out how fast it's changing with time, right? So plugging the taking a time derivative of a with the expectation value of a, right? It turns, I'm just going to write the integral form of it so we can deal with the actual wave function. Okay, when this time derivative passes through this spatial integral, it turns into a partial derivative because it basically removes all of the spatial part of that total derivative. Okay, and you can prove this in calculus if you want. But what happened is that when this derivative hits the first wave function, the wave function, well, psi dagger, right? Psi dagger depends on time. So therefore, you have to take a derivative of that times whatever is multiplied by, right? So, which is in this case, a psi, okay? We're just doing product rule here, okay? But then it also hits the second time dependent thing. Actually, before we even say that, right? Before it also hits the operator. The operator in general could depend on time, but in this case, let's just say that operator doesn't depend on time, so therefore we don't have to deal with taking the time derivative of the operator. Okay, but the second thing it hits is the second psi, right? And the second psi, right, we have to take the time derivative of that psi multiplied by the product that's in front of it, right? Which is this, right? We're just doing product rule with calculus, okay? Okay. That's how Thomson start with this, okay, without describing it, right? So Thomson is writing the same thing as what I have up there, right? You have a time derivative of psi dagger, and then the time derivative of just psi itself. But then there's these matrix and wave function between the two that's going to be interesting when the ordering of them matters, okay? And this is where I got stuck, I think, on Monday, right? Where I was like, wait, how does the Schrodinger equation help us with this, right? Well, the Schrodinger helps us with this because what we can do is that we can solve Schrodinger equation for partial psi by partial t, right? Which is going to be the operator, the Hamiltonian psi over I, right? And now I can just replace all of these partial derivative with psi with the Hamiltonian instead. Well, Hamiltonian times psi instead, okay? So doing that replacement here, so here, right, I just stick in h psi here over I. Over here, I stick in h psi over I also, okay? And that's what he did on the next step in equation 2.27, okay? He just stuck those in here, okay? Okay, so this dagger thing doesn't really do too much, except it kind of so the transposeness of this dagger, right, it's gonna switch the order after they get transposed. And you can physically demonstrate this if you transpose a matrix times a vector up on the example on top if you want, okay? The other thing it does is that instead of the complex conjugate part of it, it makes it a negative I. It changes the sign of this imaginary part, right? So, but when you have 1 over I, right? If you want to negative 1 over I is just basically I, because you can multiply the top and the bottom by I, right? And the bottom turns into 1, right? And then you just have I on top, right? So when you take your I from the denominator to the numerator, it just has a -1 effect to it, okay? Okay. Similarly here, right? You don't have this dagger thing. What are we going to do is we're going to move this I to the numerator, and that's going to bring out a little negative sign out in front of this entire term. And that's where this negative sign comes from, right? Okay. Right. So that's how we get to this part. And this starting to look interesting because, right, so there's these matrices, right, sandwiched between 2 wave functions. And these wave functions are in the same order, psi, dagger, operator, psi, right? Okay. So you can actually kind of like factorize this operator, right? Which is just HA minus AH, okay? It's known as the ha, ha. Okay. Okay. And this looks interesting is because, well, this is just the subtraction of these operators in different orders, right? And the thing is, right, in general, matrices you cannot change the order of the matrix multiplication and get the same result, okay? Okay. So the way we're going to define this is that instead of writing, HA minus AH all the time, they're going to define this as HA minus AH. We're going to call this with a little square bracket, more little brackets around, comma A. Okay, these are all operators. Okay, this is known as the commutator. Okay, so the commutator basically tells you, oh, if you switch the order of these multiplication, does it make a difference? Okay. Okay. So essentially, what happened is that if you put this in here, right, you have this little bracket stuff. It's a shorthand for the side dagger, and then the back dagger, the back alligator is the shorthand for the regular wave function with the integral all around it. Okay. So what happened is that, right, the commutation relation between the Hamiltonian and whatever this operator is times I tells you how this operator changes with time. Okay. And this is really fun because it's like basically the Hamiltonian, right, tells you how a value of an observable changes with time. And then the Hamiltonian is usually associated with the total energy, right? It's as if energy causes time to evolve, right? Cause things to change with time, okay? And this is one of the fun things that if you ever take quantum field theory, it's like, oh, this is actually something you can rigorously prove, okay? So there's a bunch of questions on these bars. Yes, these bars. Sorry, there was a question, I think 5 minutes ago. Sorry, I didn't see it.
I was just responding to it in chat. I wasn't sure.
Okay, great. Thank you. Yeah, if the chat needs my attention, let me know, because otherwise I'm not able to see the chat all the time. Okay, so this is nice because, right, if you just figure out whether or not your operator commutes with the Hamiltonian, it tells you whether or not it changes the time. So if it does not change with time, that means it does commute, right? So if this commutation relation is 0, right? If, right? Big if, right? That means whatever this observable is a constant in time, right? For example, like if you have an operation like electric charge or the color charge, those are constant with time. So these are conserved quantities, right? So whenever you're drawing a Feynman diagram, right, you have to conserve charge, you have a conserved color. In free particle, where you don't have a potential term in your Hamiltonian, this is also the Hamiltonian also commutes with the momentum operator, and then also the angular momentum operator, which is something we're going to see hopefully by the end of lecture today. Okay. These are also known as stationary states because, if something is not changing with time, they're just kind of sitting there being stationary. It doesn't necessarily mean, right, that it does not have any, spatial dependence to them, but it's just not changing. The expectation value is not changing with time, okay? The wave function can still depend on time, but the expectation value of it does not, okay? And these are like, there's a bunch of operators in Wikipedia you can look at. For example, the angular momentum one, you can see those, and we're going to talk about that in a second anyway. This table here is nice. Unfortunately, it has all these H bars in it, so if you just make those one, it'll be, so this table came from Survey where, he doesn't use natural units. So these are the various operators you will see in this class, okay? On top of that, the angular momentum operator, which we'll define hopefully before the end of the lecture today, okay? So this is a really important result, right? That whether or not something commutes with the Hamiltonian determines whether or not it's a constant in time, okay? That's what we want to try to get out of this. Yes? I don't know what I wrote up there. Just erase it. There was a question whether or not this was an actual letter, but I'm just scribbling, I think. Right. So when something commutes with each other, right? If these are, the order doesn't matter, right? Then these two things are exactly the same, right? When you subtract exactly the same thing, you get 0. Okay. Okay. When it doesn't commute, we're going to see examples of this right now. Okay. Okay. So this is kind of a neat thing where we just kind of get this commutation relation out of the Hamiltonian right away, right? And so in general, right, when let's say instead of just, the A with Hamiltonian, we just have two general operators. It doesn't even have to be the Hamiltonian, right? Right. If these operators commute, right, that means A times B and then B times A in matrix form, right? Those are the same as each other, right? That means it's going to be equal to 0. Okay. This brings up something interesting. So let's say you have some state phi, okay? And this state happens to be the eigen vector or the eigenstate for the operator A. So when you act on this with operator A, you get an eigenvalue of A, little a, right? Just a number, okay? If the operator A commutes with B, that means you can switch the order of A and B and it should not change anything, right? It's the same matrix operator or whatever you want to call it, okay? So in this case, right, let's say I have the state, which is an eigenstate of A, and I'm operating it on B first, but then A afterward, okay? Since if A and B commutes, right, that means I can switch the order. So it's actually, I can actually act on it with A first and then B instead, okay? That means, right, when you act on it with A, it just turns the matrix into a number, right? Because that's the idea of these eigenvalue, eigenvector thing. It turns that entire matrix into just a number, right? So this just turns into a number. And since it's a number, it's always going to commute with whatever matrix you want. So you can actually bring it out in front, okay? What that means is that, right, this will be has an eigenvalue of A in front of this B operations in front of our original state, okay? And since this operator B on phi also gives you an eigenvalue of B, okay? This state here is actually the eigenvector or eigenstate of both A and B at the same time. Okay, sort of trying to describe that. Okay, so phi, right, is an eigenstate of both the operator A and B at the same time. Well, just at, it doesn't mean, I don't even need to say it at the same time. Okay. 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 We're going to see a case, hopefully, before the end of the lecture today, where we can actually do this, where if you have some angular momentum, you know, something spinning around, you can actually define the eigenstate as some total angular momentum and some angular momentum along the z direction. Okay, this is L. This actually square, something like that, proportional to that. Okay, and hopefully we can start that at least today. Okay, that's what this is. All these tools that we're talking about are building up to. Okay. Okay. The other interesting case is that if the operators do not commute, that's also interesting. Okay, that means A times B and then B minus B times A is not equal to 0. Okay, this actually leads to the uncertainty principle. Okay, in general, so this delta here signifies the uncertainty. So it's not like, A initial, A final minus A initial. So this signifies the uncertainty. Okay. The uncertainty in A times the uncertainty of B is always have to be greater than or equal to 1/2 times the absolute value of the commutator between them multiplied by I. Okay. Okay. Instead of delta A, delta B, sometimes these delta A, delta B are signified by sigma A, by sigma B. So if you see it in a book like this, they mean the same thing, just by definition. Okay. Because sometimes uncertainty is signified by sigma, sometimes uncertainty is signified by delta. Okay. Depending on which book you're using. Okay. So what we can do with this is that, well, let's say we have two operators, just to do a concrete example, right? Position and momentum. Okay. Do these operators commute with each other? Can we switch them and have the same thing? And this is where the book is actually gives you a nice, decent derivation. Okay. So in order to figure out whether or not these operators commute with each other, we go back up here, right? Look up what the associated operator is for momentum and the ones for X, right? Oops, kind of crossed it out, right? These two guys. So we want to do this operation of X and also, well, without the H bar, right? Partial by partial X times negative I, essentially. Okay. So that's what we're trying to do here. Okay. So this X operated, let's just do this outright. Okay. This is the same thing as saying, right? X P operated on psi minus P X operated on psi. Okay. Okay. So this P operated on psi turns into this partial derivative, right? And the other P turns into a partial derivative, but it's acting on both of these at the same time, right? Okay. 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 So when you do, so the second term is the one that's more interesting because of the product rule. Once again, going back to calculus 1 all the time, right? The product rule, right? When you do this partial derivative, right? X depends on X, of course, right? Psi can also depend on X. And therefore, when you do the first part of the product rule, right? Partial X by partial X turns into 1, right? And it splits that into just I times psi, right? Because the leftover is just psi, okay? And then this partial derivative hits the second part of the product rule, right? Where you just have I times X, right? You just bring this out front. And then you have partial by partial psi, partial by partial X of the wave function psi, okay? And luckily, right, these two exactly cancel with each other. And then so the commutation between these two operator is actually just I, right? Because this has the wave function multiplied to it. So if you take out the wave function, right, you just have I. Okay. Right. Going back to the uncertainty principle up here, right? The uncertainty on A and times the uncertainty on B has to be greater than or equal to 1/2 times the I times the commutation relation, right? Since the commutation relation is I, right? I times I is -1. The absolute value of that is 1, right? So in natural unit, the uncertainty principle tells you that the uncertainty of X and uncertainty on P has to be greater than or equal to 1/2 actually, okay? But if we put the H bar back, you get the Heisenberg uncertainty principle where it's just H bar over 2, right? Okay. Similarly, you can see the same thing if you do the uncertainty principle with time and also, well, energy, but the energy is actually just a Hamiltonian, right? Okay. So the key takeaway in this little section is that besides, just being able to derive the uncertainty principle from just commutation relations, right? These commutation relations are very important. It determines, right, what are measurable at the same time, right? If something commutes, right, let's say A and B commutes, you can measure A, the value, whatever A is, at the same time as B, okay? The example that we're going to see in a second here, you can measure the magnitude of the angular momentum in something and the Z component of, let's say, one of the component of the angular momentum at the same time, okay? But if they did not commute, then you cannot do that anymore, okay? So that determines whether or not something is measurable at the same time and has this shared eigenstate, okay? So if they share an eigenstate, you can label them, right, with their eigenvalues, right, A and B, okay? Or the variable that represents their eigenvalue, because in general, the eigenvalue could be multiple, many different values, but, so the operator A has an associated set of eigenvalue of A's, right? Where operator B has an associated eigenvalues with the values represented by B, okay? If the operators don't commute, you get something more fun out of it too, because you can apply the uncertainty principle between the two, right? Which is what we did with momentum and position in the X direction, okay? And of course, this, goes with the delta Y PY, right? Delta Z PZ, right? So all these directions are analogous to each other. Okay, bunch of chats. Any questions? Why did we not include the bar H bar? Because in this book we use natural units when H bar is equal to 1. So you don't have to write that all the time. But in order for it to be a quantities that we're used to measuring in the lab, H bar has some units, right? Then if you want to measure that, you actually have to unnaturalize the units, and then putting the H bar back allows you to do that. Okay. Any other questions? Okay. All right. Hopefully, I'm gonna see if I can start and see how far I get in this little subsection in Thomson. But what I'm gonna do is I'm gonna grab an entire section out of out of the survey to talk about this. Okay. So whichever modern physics book you use, right? The one I'm using here is Survey, but you can use all of the modern physics textbooks should have this section, which is going to be the angular momentum in quantum mechanics. Okay, how does that work? Okay, just to go back to more classical mechanics, okay, or the stuff from general physics. The angular momentum of something is defined by, if you, let's say you have a particle, right, that's moving in some direction with some momentum P, right, and is located at some R vector away from it, okay, right? The angular momentum vector, which is also a 3 vector, right, is the cross product of R cross P. Okay. And then if you do all this cross product stuff, what you're going to figure out is that, okay, the X component of angular momentum, right, which is this part here, right, is the position vector of, Y inside this R, right? This R has some X, Y, Z in it. Okay, times the Z component of the momentum, meaning how fast is it going upward, okay, minus the Z component, the Z coordinate times the Y position, the Y momentum, okay? And the way you remember this is that if you want the angular momentum in the X direction, all the variables doesn't have X in it. It only has X and Y's, Y's and Z's, okay? Similarly, if you want Ly, right, Ly will have no Y's in it, and then you just mix the variables up until you get, you mix the X and the Z, since you don't want any Y's, then you can find that. And usually you will get it within the sign, okay? Because you don't know which order to put it in usually, okay? Yes.
You can think about R cross P as the difference of the matrices.
Yeah, it's actually, this computation is actually, the cross product is actually what's called calculated in the determinant of the matrices. But I didn't want to get into calculating determinants because I didn't teach it to you guys in general physics. But those of you who knows how to find determinants will find this equation kind of, you don't have to memorize anything. But we just give you these in this case. So we don't expect you to memorize a lot of this stuff. Okay. Okay. All right. So that's the idea of angular momentum. You have some object moving at some arbitrary momentum P at some position R away from the central object, whatever that happens to be. So in this case, what we want to do is actually do this for a hydrogen atom. So imagine this as an electron that's orbiting a proton. Okay. Okay. All right. So we're not going to get into all this, polar coordinate conversion stuff. What we want to do is actually use commutation relations to figure out if we can measure something out of this, right? Okay. So in the homework, I think I put this in the homework. I have you guys derive the commutation relations between all these different operators. So the angular momentum in X commuted with Y is actually equal to, there's an extra I that pops out, times the angular momentum in the Z direction, okay? Similarly, Y commuted with Z is actually I times Lx. Z with X is actually I times Ly, okay? This is known as a cyclic commutation relation. So you see that, this is X, Y, Z, and then Y, Z, X, and then Z, X, Y, right? You don't have to memorize these things, but it's just nice that, oh, when you derive something, say, oh yeah, that's how it is. Okay. So in the homework, I'm going to have you derive it mathematically, meaning you have to put in your variable for X and then the momentum operator for PX, right, is partial by partial X. I think there's a negative I in front here. Okay. Right. And then X is just X, right? And then if you have PY, right, that's just negative I partial by partial Y, right? Okay. And then you can actually derive all these commutation relations just by doing derivatives. Okay. So I'm just going to kind of show you physically how why that's the case. So hopefully this will be sensible. We'll see. Okay. So let's say I have some arbitrary vector, maybe pointing. So in this plane here, let's do a different color. I don't like this. Let's do green. Green. I already have a green down here. Let's do purple. Right. Have some arbitrary vector down here. Right. Okay. These angular momentum vectors are rotating things around different axes. Right. So let's say I want to figure out, does it matter which order, whether or not I do the rotation around the x-axis first or the y-axis first, if I want to do both, right? I'm going to do a rotation around the x, and I'm going to do a rotation around the y. Okay, so if I do a rotation around the x, let's do that up here, right? The rotation around positive x, I'm rotating this vector. Let's say I rotate this by 90 degrees, right? Now the vector is over here, right? I can draw these right. Right, this is the rotation. Imagine like you have a little, you're rotating this vector up like this, right? Okay. Now it's in this XZ plane, right? Then what I want to do is actually rotate it, let's say another 90 degrees along this Y axis, right? So I'm going to rotate it around this way. Okay, so this rotation, I'm going to rotate down. Okay, and that's going to put my vector like right here. Okay. So this is the first rotation. This is the rotating around X. And then the second rotation is rotating around Y axis, right? So I ended up here, right down on this bottom plane here, right? Okay. I probably should have drawn two of these. Let's see if I can do that. Right. Let's just make everything black. I can change color. Right. I'm going to draw another version of this. Okay. This is Z. This is X. This is Y. Right. And then once again, I'm going to have some arbitrary vector starting. I'm starting with the same vector, but instead of rotating X first and then Y, I'm going to rotate Y first and then X. Okay. Right. So if I'm rotating around Y first, right, I'm rotating this way. So I end up in this plane down here. Right. Okay. It looks kind of funky because it looks like I'm just lengthening the vector, but it's trying to do things in 3-dimension, right? Okay, but now, right, I want to rotate around the x-axis instead, right? Right. So what I'm going to do is, so this is the rotation around y. What I'm going to do is I'm going to do another rotation around x. Why did I pause my share? Oh, resume share. Okay, resume share. We're okay. Okay, it's just my fat hand and the fact that Zoom doesn't allow you to hide this menu. Can I hide this thing? I don't think I can. I can make it bigger. Sorry, let's not get distracted by this. Okay. Okay. So I rotated around y to get to this point, right, which is in this ZY plane, right? And then I'm going to rotate around x, right? I'm rotating in the same direction. So imagine rotating this vector up to here, right? That's going to actually rotate it to this point up here, right? And I end up at a different place, right? Right? The order matters, right? Okay. Okay. You can do the same thing with yourself. If you rotate yourself around in left to right, and then you rotate yourself, you have to do like a little backflip in order to do that. You're going to end up in a different position afterward if you do it in different order. Okay. So hopefully that gives you an intuitive sense that, oh, why these angular momentum vectors don't commute with each other, right? It matters which order you rotate things in. Okay. However, if you take the magnitude square of the angular momentum, and you're gonna once again prove this mathematically in the class, in the homework, okay, where this magnitude is the magnitude, basically the angular momentum x squared, y squared, z squared, right, all summed up together. That's how you take the magnitude of something in 3-dimension. In that case, this operator L squared does commute with x, y, and z individually. Okay. And that's kind of fun. What can we do with that? Okay. Yes. How would you do that? So the question is is there any physical significance to having L squared commute with each of the individual components squared? Each of the individual components? The way you would think about this is that you can think about your, let's say you have some object. Let's do that in black. Right, I need my X, Y, Z axis all the time. Right. This magnitude, well, L hat square rooted. That is physically signifying basically how far the length of a vector that goes out here. That's what this is signifying. Okay. But it could be in any direction it wants. Okay. It's kind of like the surface area of a circle. Sorry, not circle, of a sphere. Right. Okay. And therefore, if you have some angular momentum pointing this way, you can figure out the length, basically the radius of that circle at the same time as one of the direction of that circle. This vector. Okay. Let me think about that. Okay. But the math will, if you do all the math, you'll get some interesting thing that, oh, they just subtract out and get 0. It's always the case. Sorry, when you compute these commutation relations. Once again, going to x equals to x, right? And then px equals to negative I partial by partial x, right? Okay. So for simplicity, what the books, most books, actually all the books decide to do is just, well, since Lx, Ly, and Lz cannot all be observed at the same time, let's just try to deal with Lz only, okay? So let's pick the Z component as the one we're going to be observed along with L square, okay? Okay, before going into that, we're going to define one more little thing, sorry. There's just a lot of definition right now. And we're going to see how all these come together. Right, we're going to define some raising and lowering operators, and we're going to see why these are called raising and lowering operators. Okay, and this is going to be in terms of the angular momentum in X and angular momentum in Y. The raising operator, we're going to define it as, let's not even think about it as raising yet. We're just going to call it L plus. Okay, we're going to see why it actually raises things. Okay, is the angular momentum in X plus I times angular momentum in Y, where L minus is the same thing, but with a negative sign instead. Okay, it's kind of a combination of both at the same time. Okay, all right. Since X and Y both commute with L square, right, the raising and lowering operator will also commute with L square. Okay, since X and Y does not commute with LZ, right, therefore, the raising lowering operator in general will not commute with LZ. In fact, the commutation relation, which you will prove also in your homework, is just the raising and lowering operator itself. Okay, the commutation relation of LZ with L plus is positive L plus. The combination relation between LZ and L minus is minus L minus. Okay, and there's a bunch of operator math. Little math you can play in the homework to prove all this. Okay. And then once again, there's this one more little algebra step. You can rewrite, instead of writing L square as Lx square plus Ly square plus Lz square, right? You can do a bunch of algebra and put L square in terms of Lz and L plus minus only. Okay. Okay. The useful thing, once again, we're going back to this commutation relation, whether or not something commutes or not is important, okay? Since Lz and L square commutes with each other, right, we can define some eigenstate. In fact, I'm going to write it out like this, right? Come on, let me write. Right? Where we're going to define the variable for the eigenvalue for L square as lambda. You see this, right? Where you have an operator acting on the state, it gives you the same state multiplied by lambda, okay? So lambda is the eigenvalue associated with L square. Okay. L square, okay? And then this label M is the eigenvalue for LZ, L square, right? It's just labeling the state, right? They share the same eigenstate, right? Because they commute with each other, right? You can measure both at the same time. Okay. Now let's consider, just to get through the mathematics of this so we can do some calculations, right? We're going to define some new state, psi, where is the eigenstate of the L square and LZ, but after it has been acted upon by L plus. Okay. But remember that, right, up here, right, L square commutes with everybody, right? It's just a very nice person. Okay. What you can do is then, well, if I stick this whole wave function in here, right, psi is just this, I stick it in here, right? That's the same thing as L plus acting on the eigenstate first, and then L2 acts on it, okay? But since they commute with each other, I can switch the order, right? When I switch the order, right, this L square will pop out a lambda, right? You can basically, L square has an eigenvalue of lambda, and therefore that lambda pops out. And since lambda is just a number, you can switch the order and bring it up front. Okay. All right. And this is our original psi, right? So therefore, right, L square acting on some state will give you the eigenvalue of L square, lambda, times whatever that state is. Okay, let's just restate this over here. Okay, so we can see it without all these equal signs all the way in front of each other, right? Oops, I forgot the psi in the middle, of course. Psi equals to lambda psi, right? Okay, all right. Let's see what happens when we try to do this with LZ instead. Okay, doing the same thing with LZ, right? Remember, LZ does not commute with L plus, and therefore we're going to have to deal with the commutation relations. Okay, so if we stick in our psi once again, right, what's going to happen is that using the commutation relations up here, right, LZ with L plus just gives you an extra L plus. Okay, okay, so that's where this extra L plus comes from. Okay, okay. What you can do is that while you have an L plus here, you have an L plus here, right? I can factor out this L plus first. I wish the book actually show you this intermediate steps, right? Because it's not 100% clear what's going on. It's LZ plus 1 acting on lambda M, okay? Right? While 1 acting on, okay, you should think about this as like the identity matrix, right? Right? 1 times something always gives you 1 as, sorry, the identity operator acting on some state will give you exactly the same thing back, okay? Right, just like 1 times X is always going to be X, right? Okay, right, so this gives you 1 as the as basically the value with the original state. We're not going to change that, right? LZ, what does that give me when I act on it on a state of lambda M? Does it give me, it gives you M, right? Because, right, the eigenvalue for LZ is actually M. Okay, so you get M plus 1 here. And then once again, we're going to switch the order again, just factor out this M plus 1. And now we have L plus acting on that state. And remember, L1 acting on that state is just psi itself, right? This is just psi once again. Okay, so LZ, right? I'm going to write this on the right-hand side here. Acting on some state gives you M plus 1 times that original state. Okay. Now we can kind of start to think, oh, this is what's known, the reason why this is called a raising and lowering operator, okay? Because remember psi, M plus 1, right, is the eigenstate plus the rate, the L plus operator, right? Right. So this seems to, instead of giving you an M, it gives you an M plus 1. It increased the M value by 1, right? Okay. So what that allows us to do is do a bunch of algebra steps, Where, well, we know that L square on some state, instead of calling it lambda and m again, we're gonna try to figure out what this lambda actually is, okay? Right? By replacing L square with this other algebraic function up here, right? Where you have a plus minus operator, okay? Okay. So be really careful. We replace, instead of lambda and m, we replace lambda and L, okay? We're going to see that L, this little L is actually going to turn out to be the magnitude of the angular momentum, okay? What's going to happen is that when you act on this with all this stuff, okay, what happens is that when you act L minus and L plus at the same time, you get 0 because the raising operator raises it by 1, and then the lowering operator lowers it by 1, and then nothing happens, okay? And then LZ, right, will actually give you the angular momentum in the Z direction. In this case, we're going to call this L is going to be equal to M, okay? And then LZ square, right, because we have this piece here, right, going to give you L squared back, okay? So whatever this lambda happens to be, has to be equal to L times L, well, once again, intermediate steps, right? L plus L square, right? If you factor out this L, you're going to have L plus 1, right? That's what this equation is. Whatever this lambda happens to be, it has to be equal to L times L plus 1, where L is actually the magnitude of the angular momentum. Okay. Basically, if you do this square thing, right, you get lambda. Instead of getting lambda, you get L squared, L times L squared instead. You get, yeah, is, and then square root the whole thing. You get that's the magnitude of this angular momentum. Okay, I think I'm way over time. So we'll talk about how we do a few more mathematics with this on Friday, and then wrap up with just a discussion of the Fermi golden rule. And I think I noted in the reading, so the book does a whole derivation of the Fermi golden rule. We're not going to try to follow every step of that because it's just get into the minutia of quantum of all this quantum mechanics math that needs to be very carefully done, and I probably won't be able to do it in a lecture very clearly either. So what I'm going to do tomorrow is we're going to discuss, this transition from some higher state to lower state as an example of what the Fermi golden rule actually tells us. Okay. All right. Thanks. Any questions before we wrap up today? Stop.